Okay, in this video we're going to take a look at thermal analysis in Abaqus. We're going to do what's called an uncoupled thermal stress analysis, where we're going to compute a temperature field and then take that temperature field and use that in a constrained situation in order to calculate stresses caused by this change in temperature of this object. We're going to need to use temperature-dependent material properties. We'll talk about those a little bit. We're going to use an option in Abaqus called the material library. That'll help speed things up a little bit when you go to do your analysis. And we're going to talk about initial temperatures versus reference temperatures for material properties in this type of analysis. We're going to discuss some issues with the units that we have to be careful about. And probably in a part 2, we're going to look at reading and writing to an output database file for temperatures. Now, some of our properties that we're going to need for our thermal analysis include the thermal conductivity, specific heat, and the film or convection coefficient. All of these can be functions of temperature. We're going to use a constant convection coefficient. The density of the materials can be very important. Kind of affects its thermal impedance, if you will. And for stress analysis, we need the modulus of elasticity and Poisson's ratio as a function of temperature. We are still going to be doing an elastic stress analysis, but you could do a nonlinear analysis for the material properties as well, with elastic plastic material behavior. Alright, so there's a few things we need to talk about before we dig into this. The model that we're going to use is the same one that we did on homework number 1, that pipe. We did a 24-inch Schedule 80 pipe. That's typical type of pipe that you'd see in a power plant. I've done a little consulting for power plants locally, and computing thermal stresses and so forth. So I want to share with you some of the techniques that are involved in that. Okay, let's call up Abaqus. And what we're going to do is open up our old model that we had. Let me find it. Copied it over to my homework 6 folder. And this pipe without a seam is the one we're going to use. We're just going to load that up. Oh, it's being used by another process, so hang on. Okay, let me try this again. Pipe without a seam. And it can load that up now. When I make these videos, I try to practice everything beforehand, and kind of like the cooking shows where they put something in one oven and pull out the finished product in the other. I kind of have a finished model on deck in case I make a mistake somewhere. Alright, so here's our pipe without a seam model, and I'm going to just delete this empty one, get rid of that. And before I do much more, I want to make a copy of this, and I'm going to name this O2-pipe stress, and the original one, I'm going to rename this as O1-pipe thermal. So because we're doing a decoupled analysis or an uncoupled analysis, we're going to have one thermal analysis, and then we're going to have one stress analysis, and I name them 0, 1, and 0, 2 just to keep them in order so that it kind of makes sense to me. Now the current model is underlined, you see here, okay? And we want to load in a material from a material library. I want to explain where these material properties have come from. So let me call up a PDF file that I'll show you. And I'll get up to the beginning of this. This is something called the P22, the Grade 22 Low Alloy Steel Handbook by EPRI, the Electrical Power Research Institute. This is available. You can find this on the web somewhere. But it has lots of information in it about this particular material. Fatigue behavior, creep behavior. But the part that we're mainly interested in is this table, variation of selected physical properties with temperature. So here it is, temperature in degrees Fahrenheit. Here's thermal conductivity in BTU per hour per foot per degree Fahrenheit. mean thermal expansion with a 70-degree reference temperature. That's going to be an important thing for us to keep in mind. And here's the modulus of elasticity. It's kind of interesting. Let me make this a little bit bigger. Our modulus of elasticity goes from 30 million, like we would expect around room temperature. It changes by 1500 degrees Fahrenheit. It's only about 19 million pounds per square inch. The modulus of elasticity changes fairly significantly with temperature. Here's a chart for the variation of Poisson's ratio with temperature and some other information that we have here. Good. So I will make this handbook available to you in the group of files that I have for this analysis. Alright, so what I've done is I've taken all that information and I put that into a spreadsheet that I will also make available to you. And in that spreadsheet, here's the BTU per hour per foot per degree Fahrenheit and the temperature. And I've converted that into the units that we need for our unit system. All right, so better check me on this, but I have my EnduraSim table, and here we have conductivity. I'm going to bring this over here. So here's conductivity, BTU per hour per foot per degree F, and that is equivalent to this 1 BTU is equivalent to 0.2161 inch pound force per second per inch per degree Fahrenheit. 0.2161. So I've gone in here and I've taken this value, multiplied it by 0.2161. So I have this particular unit here in green. Here's the modulus of elasticity and Poisson's ratio, where it's a function of temperature. Here is the specific heat, and I've converted that into units appropriate for our system. And then the density of steel, 0.284, I need to convert that to snails per cubic inch. And last but not least, here's the coefficient of thermal expansion, and I probably ought to put in here 70-degree reference. I'll explain what that means soon, I think. So I'll save that file. So I copied and pasted that into Abacus. Now the material properties that we had used previously are very basic. Here's our Young's modulus and Poisson's ratio. That's all we used last time, and we said it was a constant temperature. Didn't worry about that. But now when you click on this, see this extra button that's come up? It says Material Library. Now you'll need to search for your material library, but I've named one called materials.lib. I think that should go in your temp folder. Okay. Should go in your temp folder. But in here it is P22 steel, and I said corrected for our unit system. So I'm going to highlight that, and I'm going to click on this button, Add Current Material Model to this. So there it is. And I want the same information in the pipe stress model, so I'm also going to do that and add that to that model as well. Oops. I need to make sure I selected it as a current model. See, it's not underlined. So kind of like double clicking on it, it underlines it. So now when I go here, I ought to be able to do that. Let's just verify these material properties. Here's our conductivity. Here's our density. Here's our modulus of elasticity as a function of temperature. Here's our thermal expansion, and there's that reference temperature of 70. We'll explain it again, and we'll explain what that means soon. Here's our specific heat values. Okay. Now, I want to avoid any confusion. I want to get rid of this one. That came from our previous analysis. All right. Now, let's look into this thermal. Now remember, we had specified the previous material properties in our section definition. So we're going to go into section. We're going to open it up, and it gives us a warning, says our material no longer exists. So we're going to select this P22 corrected. And we're going to come down here into the stress job, and we're going to do the same thing before we forget. And by we, I mean me. Alright, so here, now we got that settled. The other thing we need to do right off the bat is there are different element types for different types of analyses in Abaqus. There's a stress analysis element, and there's a thermal analysis element. And there's a coupled thermal stress analysis element. We need to change the current value definition of our elements from a stress analysis to a thermal analysis element. So I'm going to go into this thermal one, I'm going to highlight that, and I'm going to come over here, I'm going to go down to mesh. You see this one says S4R, assign element type. I'm going to click that, and I'm going to select the regions individually. And I'm going to scroll down in this box until I see heat transfer. And then the defaults down here are fine. Linear, standard, everything's fine. So it's going to be a DC3 D8. So it's a three-dimensional, 8-noded continuum element, and then D has to do with the heat transfer. And then hit OK on that. So now we change that element type. Alright. So the basic idea that we're working with here is if this is going to be a steam pipe, there's steam that's going through here. And that steam has a certain temperature. And it's pretty easy to measure the temperature in a steam pipe. It's a fairly common process variable or parameter that's measured during the operation of a power plant, for example. Now that steam comes through here and it touches the wall of this pipe, and then it heats that pipe up, and that gets conducted through the thickness of the pipe, and it may also be convected away from the outside edge of the pipe. If there was a cool breeze on this pipe, you can set up a convection coefficient on the exterior of the pipe to take that heat away. Now in reality, in most power plants, there are insulating jackets around these pipes. You really want to keep all that energy in that pipe. You use that to drive the turbines. So we're not going to put a convection coefficient on the exterior of the pipe. That's going to be like an ideal insulated area. But we are going to put a film coefficient or convection coefficient on the inside of the pipe. Let's see what our steps look like first though. So we're in the thermal part. Let's do the steps. Now this step we had was from the stress analysis step from our homework number 1. Let's just get rid of that. And let's see what's in our initial step. We have some boundary conditions. We can leave them in here if we want. We might as well delete them. Boundary conditions are ignored in thermal analysis, pure thermal analysis. So let's see. We might have to open up the manager and then hit delete on this. That's fine. Alright, so we're going to start our pipe off with an initial temperature. And I'm just going to pick 700 degrees as a Fahrenheit as an initial temperature. Just a number I'm picking. And you know, maybe that's a steady state value that just happens to be 700. So I'm going to click on this predefined fields. And here it says mechanical, and then fluid is kind of grayed out, and it says other. We're going to go with other, and then temperature, here's highlighted here. There's some other options for different types of analyses. You can hit continue. And select regions, I'm going to choose individually, and I'm going to just set the entire section of pipe equal to a constant 700 degrees Fahrenheit. Alright. Now we're going to create a second step, guess it's called step 1. It's the one after the initial step. And we are going to look for heat transfer. Here it is, right here, heat transfer. And the time period is 1. Now remember, we're in the seconds system. And there's a fair bit of thermal inertia in a pipe. So if we do this in like 10 seconds, the heat may not transfer from the inside of the pipe to the outside. So we're going to change our time period, and maybe we'll make this like an hour. So let's call this 3600. And it has an option here for steady state or transient. We're going to choose steady state for our first one. Now it has a little warning that pops up: default load variation with time. It's been changed to ramp linearly over the step. Incrementation, let's add an extra 0 or 2 on the end of that. And we're going to hit OK. Now we need to set up this film coefficient or convection coefficient, and that is in interactions. So we're going to create an interaction in step 1. Here it is. In step 1, we're going to create an interaction. And we're going to do a surface film condition. I'm going to select the regions for the surface. Now, right now I had it set on individual from the previous thing I did, but I'm going to change this by angle. And I'm going to select the interior surface of the pipe. I'm going to select Done. Okay, the film coefficient, let's take a look at what we're going to use for that. Now, I have a website that I found that is kind of interesting, and I made a PDF out of this page, and I'll provide that to you. But this comes from TLV. This is a steam specialist company. And it has different values for these convection coefficients. And so for steam, it's between 6,000 and 15,000 watts per square meter per degree C. Okay. And we need to convert that to our unit system. So I just picked a number of 10,000. It's in between those two values. And here's our conversion factor. I went back to our EnduraSim table, and I found the right conversion factor for convection. Right, watt meter squared. It says Kelvin, but per degree C or per degree Kelvin, same thing. And here's the coefficient that I need to multiply that number by: 3.172 times 10 to the minus 3. So if I do 10,000, I get 31.72. So I'm going to specify a film coefficient in here of 31.72. You can have an amplitude on the film coefficient itself, but we're going to just leave that alone. We're going to have a sink temperature. We're going to specify 700 degrees. So that means that the steam is at 700 degrees. And we'll just leave this as ramp, and everything else should be okay. So basically what I'm trying to do is just equilibrate our pipe to a particular temperature. Now I kind of did that already with the predefined field, but it's not a bad idea to do both. So your predefined field, maybe you start your pipe off at 70 degrees for your predefined field for room temperature, and then with your steady state analysis over a long period of time, you have the steam be at 700 degrees, and then it transfers into the pipe. But we're just going to set this up as if it's at 700 degrees. Alright, so now we're going to create a step 2. It's going to be heat transfer step. And now I want this to last a couple of hours. So I'm going to specify 7,200 seconds. And it's going to be a transient analysis. Now I need to go to the incrementation tab Let's make this 10,000 increments just to make sure we don't run into that error. And a maximum allowable temperature change per increment, I'm going to put 25 degrees Fahrenheit. This is a number that if you make it too small, it's going to have convergence issues. If you make it too big, then it's just going to be too coarse of an approximation. I'm just going to use 25 right here, and I'll leave the defaults for everything else. But I do want to make this time period 7,200 seconds. Alright. Now, in our interactions, we want to modify this interaction. We're still going to use this film coefficient. Sink definition is going to be uniform, but we want to specify we're going to create an amplitude. We're going to create a tabular amplitude, and the one that we're going to use is one I'm going to provide for you. You can make your own later if you want. But this one is going to go from 700 degrees Fahrenheit. It's kind of important that this start out at your steady state temperature. And it's going to ramp it up. And it's going to go to 1050. And then at 3600 seconds it's at 1050. And at 7200 seconds it still stays at 1050. So we're going to let it kind of calm down a little bit. But to get this in here easily, what I'm going to do is I'm just going to highlight these columns. I have seconds in the first column and temperature in degrees Fahrenheit in the second column. And select copy. Now come over here and paste. And we're done. Easy as that. Now, be careful here. Just because you created an amplitude doesn't mean that you've chosen the amplitude. So now you got to choose the amplitude. And this value you have to be careful with too. We need to change that to a value of 1. The way this works is kind of like what we saw with our loads when we did our plate with a hole example. It takes this value, multiplies it by the amplitude to get our temperature. So if we left that at 700, then it would start out at 700 times 700 degrees. We don't want that, so we need to change that sink temperature to 1 when we use the amplitude card that we just defined. Alright, so now we have that, and I think we are ready to create a job and submit it. But let me save this. So I have this here, and I'm just going to make a new name for this. Uncoupled thermal. Okay. Alright, so I believe I have everything we need. If I don't, we'll probably find out pretty soon. There's a couple jobs in here. I'm just going to delete these job names. Not really deleting the data associated with it, but I don't want to get confused. Okay, and just to double check, we are in the pipe thermal model. So I'm going to create a job. It's probably a good idea. There's the source. Let's call it something more descriptive. Thermal. Okay, fine. Alright. Everything else in here is fine for defaults. And then I'm going to right click and I'm going to hit submit. Now it has a little complaint that we don't have any history output in. Tell you what, let's hit no, because there's one thing I forgot. I want to change the output field request, particularly in step 2. Let's change this to every 10 seconds. Now, that's going to output quite a bit, but that's okay. Here we have the heat flux, the nodal temperatures, and the reaction flux. That's fine for what we have here. Okay. All right. Now let's do this. And we're going to hit yes and ignore that history output warning. So it's going to take just a few moments to do this. But while that's working on it, let's talk about the mechanics of materials, about how to calculate thermal stresses. So let me get back to my screen here. Let me save this page. And you might remember in mechanics of materials, you probably did thermal analysis. And if you have something fixed in between two walls, it's got a coefficient of thermal expansion, and it's subjected to some change in temperature. There's some modulus of elasticity. There's, I guess, let's see, some length to this, maybe some cross-sectional area and all that. Well, the total deformation, if it's fixed in between two walls, is going to be 0, but that total deformation is actually composed of two parts, a mechanical deformation plus a thermal deformation. Now the mechanical deformation is the FL over AE term, and the thermal deformation is alpha delta T times L. And if that's equal to 0, we can rearrange this and if we notice here, the lengths cancel out on both sides, and the F over A term that we have is the stress. The stress due to complete thermal constraint is minus alpha delta T times the modulus of elasticity E. Now we know the modulus of elasticity can be a fairly big number. It's really easy to get very high stresses when you have thermal constraint and you're heating things up. Mechanical constraints and you're heating it up. Okay, so this is our formula that we're going to use to check our abacus results when we get to the stress analysis portion. I have a feeling our thermal part is done, so let's take a look at it. Okay, so thermal is completed. We're going to right click and get into results. Now this comes up as a primary variable as the heat flux, but what we want to change that to is NT11. And we're going to hit the animate button and see what happens. So here's our time that's increasing. And let's see. Doesn't look too interesting. Let me see what might have happened here. Okay, I see what I did wrong here. I mixed up, I was clicking on the wrong spots. So for my interaction 1, I want to have a ramp of 700, because that's my steady state analysis step. Let's just double check that, yeah, steady state. And for this one, I want this to be the transient, and in this one, I want to have, this is the one I want to put the 1, and I want to choose my amplitude 1. Alright. And let me just check my film coefficients. We might bump those up a little bit. Alright, so I understand what we need to do now. I'm going to change this time period in step 2 to 7200, and if I didn't already, we're going to change our amplitude card, and we're going to add a last spot to it, 7200 and 1050, and that should do it. We're going to leave our interaction term as it is, 31.72 and everything. Okay, it's getting a little bit late at night, get a little bit punchy. We're going to submit this, and we're going to overwrite those files since I'd run it before, and it's going to take a few moments to go through this. Now while that's going, let's talk a little bit about the coefficient of thermal expansion. We're going to use that in the stress analysis task. And for that, I'm going to get to our abacus manual section. Here's some details on film coefficient. You can search for that. Okay, there's reference temperature for the sink. And here's the section. I did a Let's search for thermal expansions. Section 26.1.2 in our manual. So thermal expansion, material property included in the material definition, and it's kind of interesting the way they define this thermal expansion. So the coefficient of thermal expansion can change with temperature, and here is the thermal strain versus temperature chart, and they show this curve. Let me go back to our sketch pad. Okay, I've done thermal measurements, thermal strain measurements before. They're a little tricky, but not too bad. And so over here is temperature. Now, Abacus calls temperature theta, and the reference temperature is theta 0. Now, typically you might think that our reference temperature might be room temperature, and indeed it is for our coefficient of thermal expansion for our steel. Remember, I pointed that out in the P22 handbook. Now, the interesting thing is coefficient of thermal expansion isn't constant with temperature, it changes. So maybe it does something like that. So at room temperature we get a certain value for the coefficient of thermal expansion, and at some other temperature we get a different value for the coefficient of thermal expansion. And the way that we get that is by applying alpha delta T, and then we can solve this for alpha if we would like. So one way to think of this is the rise over the run. Now at that particular point, that's like a secant value. It's the slope from here to here. And if we go to a different point up here, that changes. Now if you're familiar with metals, there's two ways to define a slope in the nonlinear region. One is with the secant, one's with the tangent modulus. In some cases you may be given a tangent modulus and you need to convert this into a mean value. Okay, so what Abacus needs is defined by the terms in red. Now the reference temperature might be 70 degrees. Maybe you're doing very high temperature work and your reference temperature might be 1,000 degrees. I don't know what it is. It depends on how that table was defined, but that needs to be set in Abacus. And Abacus is it makes sense once you see it, but it's a little bit weird how it does thermal strains. And the key is this equation right here. Let me write it down on this other page. Let me use blue. Abacus computes thermal strain by this formula. It's the coefficient of thermal expansion times your current temperature minus your reference temperature minus coefficient of thermal expansion at an initial temperature minus your reference temperature. Now we're taking our pipe up to 1050 degrees Fahrenheit. So for us, our thermal strain is expected to be coefficient of thermal expansion at 1050 degrees Fahrenheit times 1050 minus our reference temperature of 70 degrees Fahrenheit. minus our coefficient of thermal expansion at our initial temperature, which for us is 700 degrees Fahrenheit, times the initial temperature minus 70 degrees. So we'll compute this number and we'll see what Abaqus comes up with. But let's take a look and see if our thermal analysis is complete. Okay, it is. We're going to right click this on, look at results. We're going to go up here and make sure you change this to NT11. Okay, and then we're going to animate this. And there's a lot of steps in this, but you see it's heating up over time, and the heat is transferring through the wall thickness of this pipe. And at 3600 seconds, we ought to be at our 1050 on the inside surface. And then as we move to 7200 seconds, it starts to go through the entire wall. So that extra time I put at the end was just to make sure that we have a uniform temperature in our pipe. But you can do general transient thermal analysis. Okay, now it's just starting over. Okay, so that's where I want you to get for the thermal part. Let's pause this. And now we want to set up our model for the stress analysis part. So let's minimize this display, and we're going to go into the pipe stress part. Okay, we have our material property in here. We have our step. Okay, we have an initial step, and our predefined field. This is going to be our initial temperature. So we want to set this temperature individually to 700 degrees. It's important that we do this in this step. Okay, in our step 1, we want to come in here and we want to make sure that we set up our boundary conditions also. So let's get in here in boundary condition 1, and we're going to add a boundary condition. It's going to be based on displacement. And now we have the right edge fixed, but we're going to go by angle, and we're going to fix the left edge. It's kind of hard to see. These little squares mean we have a predefined field. Okay, those are highlighted. We're going to hit done. We're going to do U2 and U3. And we're going to choose our coordinate system to be our cylindrical coordinate system that we had defined. So we're going to allow it to expand in the radial direction, but we are going to keep any rotations and any displacement in the z direction. So now we have this fixed in between two walls. We're going to hit OK on that. Okay, so now in our step 1, let's expand step 1, we're going to create another predefined field. It's going to be based on temperature. We need to get rid of that load, but we'll do that in a moment. We're going to select the region for the predefined field individually. And on this drop down, we're going to do from results or output database file. We're going to choose our file name. Now we called this one thermal. And the step to which we are going to start our analysis is step 2. So when we started our transient analysis. And the mesh compatibility will be compatible since we're using the exact same mesh. We're going to do that. Okay. And since we stopped our analysis after step 2, then this is all we need. We're going to hit OK. Let's get in here on loads, and we'll get into the loads manager. And let's delete this. And I think we are ready to run. So let's create a job. I'm going to call this job stress. Let's get into our step, and we need to change the time period. Okay, we want the time period to be 7,200 seconds. Let's put a couple zeros after our incrementation. Our field output request, let's have it need to change that to every, I guess 10 seconds. That's going to be quite a few, but that's the same as what we had in the stress and the thermal analysis. And in our strains, let's also choose THE, the thermal strain components. Okay, here we have all this other stuff. And let's do E for total strains. I don't think we need plastic strains. We can leave those selected, but we're going to E and THE. And everything else looks okay. Let's see if there's anything I'm missing here. I guess we'll find out soon enough. But I'm going to go down to my stress job and I'm going to click submit. Alright, so let's go back to our page. Let's see if we can compute this number. So the coefficient of thermal expansion at 1050 F is 6.95 times 10 to the minus 6. This should have been an epsilon TH. Now the difference between 1050, which is where we're going to, and 70 degrees is 980. Now we're going to take and subtract off coefficient of thermal expansion at 700 F, 6.62 times 10 to the minus 6. And we have 700 minus the reference temperature. That's 630. Alright, so let's do the calculation. Alright, and I get the number 2.64 times 10 to the minus 3. Now the mechanical strain will be exactly equal and opposite to this number. And so the stress that we would expect in the z direction would be negative 2.64 times 10 to the minus 3 times the modulus of elasticity at 1050. Modulus of elasticity at 1050, let's find that, is 23.9 times 10 to the 6. So I'm expecting us to get a stress, and fingers crossed, this will all work out, for around 63 63.1 KSI. Alright, let's see how we're at on our job. Okay, the stress job is completed. We're going to right click and look at the results. We're going to change this to S33. And look what we got. about 6.3, the interior, minus 6.3 times 10 to the 4, which is 63.0 KSI. Let me find my sketch pad. And I'll kind of write them down at the bottom here. Alright, 63.1, 63.3. I'd say that's pretty good. Now if we want to animate the temperatures or the thermal stresses as a function of time, we can do that. And they're not changing a whole lot, but they're changing a little bit. And you can see it. The pipe is growing in the radial direction. This is an exaggerated deformation. And the stresses are varying with time. The higher thermal stresses in magnitude are the bluer ones. So the red is kind of a low thermal stress, and then the blue is more compression. Yeah. So so far so good. All right. Now I think this is good for this particular video. We're going to stop this here, and then probably in a separate video I want to show you how to read and write temperatures to the output database. And in fact, given the hour that it is here for me, and then I've been at this all day, I'm going to refer you to a couple of videos that I have made previously, and you can watch those, and I'll probably try to make a very short video for this specific geometry that we have here.